Here we could look at the difference between an Earth-centered datum or a global referenced ellipsoid, or you could look at a local datum, which is a local referenced ellipsoid. So the global Earth-centered datum here is in blue, and the geoid here is, let me draw again, is in black. So you could see the geoid, also known as Earth's surface, is right here, and we could say that's irregular. And the local datum, also being locally referenced, is the red dashed lines. So we could see here that the Earth-centered datum is located in the center of Earth's mass, and it fits better globally to the geoid. You could see it fits here, and it fits closer compared to the, let's say, the local datum of NAD 1927. We know that the origin of NAD 1927 is based in Kansas compared to the center of Earth's mass. So we could see here that here in this part, the NAD 1927 matches this part of the geoid or Earth's surface. But here in this area, it doesn't do a good job. So again, it's important to use the best datum and the ellipsoid that's attached to it. So again, these are examples of datums, survey benchmarks. An example of a benchmark, there is no single standard benchmark. They all include what they are: a height above sea level, and a cross or point in the middle for a surveyor to place the point of their survey equipment. Again, these are the horizontal Earth datums. And again, an Earth datum is defined by an ellipsoid and an axis of rotation. So we know that the NAD 1927 datum is retired, but this used the Clark 1866 ellipsoid. And we have the NAD 83 that replaced the NAD 1927. It has more accurate geographic coordinate points, and it uses the GRS 80 ellipsoid. And the WGS 84 uses the GRS 80. So it's almost the same as the NAD 83. And again, common datums: NAD 1927, NAD 1983, and WGS 84 and GRS 80. So over time, data collection technology improves, and also we know that land and ocean masses, they move and fluctuate over time. And because, you know, this changes, our geographic coordinates for a specific datum are going to alter. So that's why NAD 1927 was replaced to the NAD 1983, which is more current, or the WGS 1984. But currently, NAD 1983 is getting replaced with a more accurate geographic coordinate datum. So again, the NAD 1927 uses a Clark 1866, which is a local reference ellipsoid, and the NAD 1983 and WGS 1984 use the same global referenced ellipsoid based on the origin and the center of the Earth. Again, our ellipsoids, we know there's different ellipsoids like we see here because of the different semi-major axis and the semi-minor axis for each ellipsoid. And we could see how they vary at the equator axis here. So at the Clark 1866, it's 6,378,206 meters. And for the ellipsoid that was located in the center of the Earth's mass, it's 6,378,137 meters. Again, we know this one is more accurate compared to the other. So again, a datum shift is when the coordinates associated with the benchmark and the resulting control points is adjusted or changed based upon either better surveying techniques, better mathematical calculations, or adjustments for continental shifts. So here we have a reference point for a spheroid. So here we have the spheroid's position in relation to actual Earth. And we could see that this datum will be accurate to the point where it touches the edge of the Earth. So this local datum, this spheroid or ellipsoid touches the edge of the Earth and it's a good fit there. But again, it's a bad fit here on this side. Bad fit. And when your ellipsoid is based on the center of Earth's mass, again, it will be a better fit to be matched globally. So this is a best fit all around the Earth. Here is an example of position shifts from datum differences. These are the different types of datums, and again, as we learned, these datums are attached to different ellipsoids. And we have the WGS 84 longitude coordinates, and it's labeled here as a star. And we could see that according to the WGS 84, this is the accurate representation of the Texas Capitol Dome. So that's the benchmark for the Texas Capitol Dome. But if you were to use for example, a Tokyo datum and their referenced ellipsoid, you could see that your location of the Texas Capitol Dome is about close to 1,000 meters off. So that's why it's very important to use a global referenced ellipsoid and an attached datum to it. Or if you are focusing, let's say, in Tokyo, you'd want to use the Tokyo datum and its attached ellipsoids to get an accurate position of the geographic coordinates. So these are the geographic coordinates below are for the city of Bellingham, Washington, using 3 different datums. So again, NAD 1983 and WGS 1984 datum uses the globally referenced ellipsoid. So the origin is based on the center of the Earth's mass, whereas again, NAD 1927 uses a different ellipsoid that's local. And it's based on a fixed location on Earth, which we know is Kansas. So we could see here the difference for the longitude, negative 122.466. And then for NAD 1983 and WGS 1984, we could see negative 122.468. And then again, it starts getting different the further we go down in decimal value. But NAD 1983, because it's using the same type of ellipsoid based on the center of Earth's mass, it's similar, very similar. Negative 122, 46, 8, 1, 8, 3, 5, 3, 7, 9, 3. So it's exact. Whereas in the latitude, it looks like it could differ a little, but we know definitely there's a difference between the NAD 1927 compared to the globally referenced ellipsoid and their datums. So again, the underlying datum and spheroid to which coordinates for a data set are referenced can change the coordinate values. Here we could see the white lines are the roads in NAD 83, and then the photo is in NAD 27. So again, NAD 83 is more accurate position compared to NAD 27, and also we know that because it's using a globally referenced ellipsoid, which has a better accurate representation. So at the center of Earth's mass. So you could try to match up these roads here with the photo, but you could already tell that it's off by a lot. And another thing I want to go over is that, again, looking at the different coordinates with NAD 83 and NAD 27 for Esri Redlands. So when it comes down to the seconds, it differs for sure. And then we already know that NAD 83 is globally referenced ellipsoid, while NAD 27 is a local referenced ellipsoid. So as a recap, angular measurements is our latitude and longitude. An example of ellipsoids are WRS 80 or Clark 1866. And datums, examples of datums are WGS 84, NAD 27, and NAD 83. Lastly, I want to go over this figure is a graphical explanation of ellipsoid height, orthometric height, and geoid height. So we could see here, again, our geoid is in red. And this is the average mean sea level. And our geoid can either be above the ellipsoid, like we see here, or it could be below the ellipsoid. And in this example, our ellipsoid is WGS 84, again, a globally referenced ellipsoid. And then we have our Earth's surface. So the geoid is not going to be the same as the Earth's surface because we know the geoid is going to be a surface that represents where sea level would be if this ground surface was not here. And again, it can either be above or below the ellipsoid. So based on these H's and N's, the capital H that we see here, this is the orthometric height, and this is defined as a measured distance between the geoid and the Earth's surface. And then we have our ellipsoid height, which is a lowercase h, and our ellipsoid height is a measured distance between the ellipsoid and the Earth's surface. And then for our geoid height, this is the difference between the measured distance between the geoid and the ellipsoid. So again, these are the definitions, and we just went over the shape of the Earth and the model of the Earth, which is our datums, our exact geographic coordinates of latitude and longitude, and the different types of datums. Next, we're going to get into projections. So you need to have this as a basis in order to move on to the next step, which is projection, and then converting it into a flat map. So next week we'll go over projections. Thank you for listening and watching.